Good morning. Good morning. Hello, everybody. That's annoying. All right, so I need you to just give me a second here because it's been very busy here in the last few days. So I just want to make sure I've got everything up to date. And let me see how many people we have on Twitch right now. I gotta make myself a moderator or something. All right, so we have maybe, let's see, 11 people sitting here. So I'm just going to take one moment to talk about assignment 6. So I know a lot of you were on top of that, and I felt like last week I had been communicating about it quite a bit. And I do remember saying that it was going to be due on it was due on Saturday night, and then we asked for an extension, so I gave it till Sunday night, with the late deadline being Monday. And then I figured out, after I had done that, for some reason, Code Grade doesn't, it won't let you submit a late assignment, even though it's still available. And I wasn't going to take the time to figure that out, so I scrapped it. So I guess kind of without telling you, I just moved every deadline back to the late deadline. So I didn't really change the due date. I mean, I did, but it was available for the exact same amount of time. And if you ever are confused about that, you can just go to Web Campus and see what I've set up there. The Web Campus due dates are always the same. And so I just want to say the amount of messages that I got yesterday about assignment 6, especially late at night, was a little scary. And I got a ton of emails from people who didn't get it working. So I guess I want to know, is there something that happened? Because I thought that I was pretty fair on that. I really did. And, some of the messages I got, I mean, this happens more often than not, but it's pretty obvious for the people who don't come to class, because I get this question about, printing those 2 messages, or, how my Code Grade assignment got docked a ton of points because I couldn't match the output. I feel like I've been very clear on all of that. So if you think I'm being unfair in some kind of way, please tell me. But I don't know what happened yesterday with assignment 6, but right now I'm not feeling very merciful. I do go through the Code Grade assignments, so if you do end up with like a 10% and you got most of it working, I promise you I'll adjust the grade a little bit. But the rest of the assignments are out. I know it's the final week, but this is a summer class, and so I need you guys really to kind of buckle down. I need you to buckle down, Thank you for that. I think that I've been very helpful. I mean, I was messaging some of you guys up until 11:45 last night, so I'm very generous instructor, I think. So I appreciate it. So I guess I'm sorry for those of you who struggled last night, but get started earlier. This class it's only 5 weeks. And I know it may seem like a lot of work now, but it's actually less work than it is in the semester, right? One less assignment, one less test. So this week you're really going to have to kind of buckle down to get these other assignments done. I know a lot of you already have, but you know, I've got a lot of stuff to be doing too. So please get it done, you know, please do it. And I'm here to help you. And the sooner you come to me for help, the better. All right. And thank you guys all. You make me smile a lot. I don't mean to be I don't mean to be coming down with a hammer or anything here, but you know, I was kind of sad about last night, so that's all. Other than that, all of the assignments are up. All the code grades are up. All right, that's all good to go. Thank you. I appreciate it. Yeah, so assignment 7, it's up, right? And so guess what? We talked about that's due on Tuesday, right? And the late deadline is Wednesday. Well, since Code Grade's not going to let you do the late thing, it's due on Wednesday. That's your last day to do it. Assignment 8 is due on Friday. Assignment 9 is due on Tuesday. I have the code grades all set up for those. All right, I do. Like I said, I'll go through the code grades to make sure you're not getting a 0 for, like, for example, missing those 2 outputs. But you don't get started early and look at those things. And that's pretty much it. So, you know, everything for the remainder of the semester has been uploaded. Today we're going to talk about linked lists. Tomorrow we're going to talk about linked lists. And then Thursday we're going to do a whole review. And then we're going to have our final exam on Friday. All right. So be on the lookout for that. I'm just going to talk a little bit about assignment 9. Today I'm going to go over, I have to do some linked list stuff first, but at the end of class, I'm going to talk about assignment 9. Now everything in that assignment is manageable, except there's one function in there that I'll talk about. In that function, I will do part of it for you. Well, no, I will do that function for you in class. Except you'll have another option to get some extra credit on that function. So when I go over the assignment, I'll talk about that. But just like the previous assignments that have been difficult, I know that we're in the last week. For assignment 9, I will probably do the hardest little bit in front of you, and you'll have the option to make it even better for some extra credit if you want. But if you're doing that time crunch kind of thing, you might just be able to copy paste that in there and do the rest. All right, so be on the lookout for that. And let's start talking about our linked lists. All right, this is the last subject for the semester. So I'm just going to kind of go over those notes, and then we're going to spend a lot of time coding today. All right, we're going to spend a lot of time coding today. We'll add a few things. We'll probably do some whiteboards if I get the chance. I just want to see. I think that's good enough on the size. Yeah. All right. So, remember that we've been using dynamic arrays this whole time. And when I say a dynamic array, I'm talking about one that uses a pointer. And when we use those pointers, we call something like new, right? We'll say int my array equals new int, and then I say, 3 in here, something like that. And that's going to give us 3 side-by-side integers in the memory, right? It moves along that same strip of memory. So we've been doing that this whole time, and now we're introducing a new kind of dynamic array called a linked list, which are not contiguous at all. All right? They're not contiguous. They're kind of all over memory. And so because they're not side by side in memory, the main thing is, where did I put it down here? We have to remember, or we have to store the information about where the next node is. Here it is. Each node also stores an address to the next element, right? So in a side-by-side array, we don't have to do that. We know where the next element is. It's right next to this one, right? It's right next to this one. But in a linked list, since they're all over memory, each node is going to have to store that information. Each node will have to store that information. All right, so there's a few things about linked lists. Reading and writing to LLs are not faster. Hulu says linked lists are sort of like trains. That's exactly right. 2 semesters ago, the linked list assignment was a train assignment. We made trains. So yes, that's exactly right. They are like trains. You can think of the data being the cart and then the link being the link, right? There's it's like a hitch that holds the wagons together. That's what the link is. So we'll make some whiteboards today, likely. We will make some whiteboards today. You'll kind of see how those look. We did do the Excel sheet last time, but that's not enough. Today we're going to do a whiteboard. So as I said, reading and writing to linked lists are not faster, all right? They're not faster. So you say, what the heck? What's the advantage here? Well, adding a new element, there's no need for copying all of the old elements, reallocating, deallocating, all that fun stuff. All right, there's no need for that. You can just allocate a new node and link it in. That also means, if you're going to have a really, really big list, so imagine allocating a dynamic array of 10,000 elements or maybe even more. For that to be done with a pointer, the operating system would require, or we would require the operating system to have 10,000 side-by-side bytes, or whatever size of that type, right? And that might not be possible. So a linked list really it can kind of morph to any situation here. If we've got some fractured memory, there's not a lot of side-by-side memory. The linked list can hold almost more data because the side-by-side requirement, it's not there. Though it is important to note that linked lists do take more memory. So let me kind of add that in here. So linked lists require more memory in general, but not that much more. Linked lists require more memory. And the reason for that is because it's also storing the address, right? So on top of storing whatever the element is, you're going to be storing the next address. That's why. But on the same kind of idea on how adding a new element has an advantage, deleting an element has the same advantage, meaning you can just delete the node and adjust your links, right? You imagine a helicopter comes up to the train and pulls that wagon out of the train, and then they just link the next 2 wagons together there. So we did talk about this last time. Each node stores an element. Each node also stores an address to the next element. And if it's a doubly linked list, it requires even more memory. And each node also stores the address to the previous element. All right. So I talked about, in general, there's only 2 kinds of linked lists, the singly and the doubly. Though there's a variation called a circular linked list, where the last node is linked to the first node in the list. So in that way, we kind of have 4 total linked lists, in which you have the first 2 just general linked lists, and then if you make them circulars, you have 2 more options. In a list that is non-circular, the last element will point to null. If the list is circular, the last element will point to the first element, kind of comes back around. And then this is the most important part. With any linked list, there's always one pointer pointing to some node in the list. Now, in our example, we'll refer to this as the head node. We use this node to get into the linked list. So I kind of talked a little bit about SLLs and DLLs. But I asked that one question. I asked this one question here. I kind of wanted to move it up here. And this is always a test question that I ask. Of all the linked lists, which of them need a head node to always look at the first one? It's a non-circular singly linked list. All the rest, it doesn't matter because you can get, to any node from any node. In this case, you can only traverse an SLL in one single direction. Thus, you need to have that head node looking at the very beginning, because once you get to the end, you can't come back around. So I'm actually going to open up Paint, and we'll make just a little bit of an image here. We are going to continue on with the code that we were doing last time. All right. Now, I did speed run something here at the end, but I will actually just delete it and we'll redo it, because it looks like I changed some things up in there anyway. Trying to compile. All right. So, for our whiteboard, guess I'll do an invert. I like doing the inverts. And then we'll use probably a blue. Let's say Control-Shift-I. Select, delete, and then we're going to make our little wagon. So this will be our wagon here. And our wagon is going to be split down the middle. All right, so we're going to have the actual data part, and then we're going to have the link part, right? So one of these is the data, and one of these is the link. I'm going to kind of fill it in here a little bit just so we can get a nice little view. I know that's not a very pretty thing, but we'll kind of shrink it down a little bit and put it here, all right? So this is going to be our little linked list. Looks kind of like a magnet. Artist Mr. Petrowski here. And we're going to write some things in here. So let me pick a good color. I guess this will be red for fun, and I'll say that this is the data. So whatever value is stored in this data, I'm going to make it just a little smaller. That's a little too small. And then the red part's going to be the actual link. All right, and so what we call that is next, usually. We just refer to that as next. And the next is a pointer. So what I'm going to do is I'm going to keep that kind of up here. And then I'm going to have to kind of delete my stuff here. I was not thinking ahead very well. So in our example today, I'm actually going to make this list that we do on the whiteboard. That's exactly what I'll do. We'll do it in main so you can see exactly how it works. And whenever I'm coding something, I'm going to try to imagine it for you. I'm going to try to show you exactly on the whiteboard what's going to happen. So we're going to pretend today that I'm making a singly linked list to start, the most basic one. And say it's going to have 3 elements in it, all right? Say it's going to have 3 elements in it. Now we can make it a little bit bigger for everybody. I think that's fine. And so we made it a template, so we'll pretend that we're working with ints for now, all right? We'll pretend that we're working with ints. So let's say we've got, a 3 in here, and then maybe a 4 and a 5. Doesn't matter too much. And each of these nodes needs to point to the very next one. So we're going to have a little arrow here. I'm going to make them green. And they point here. Now, where's this last one pointing to? If we're going to do a singly linked list, where's this last one pointing to? And this one up here we're going to call our head node. Where's this one going to point to? What do we say in the notes here? This is not a circular linked list. So how do I know if I'm at the end? What do you think I should initialize that to? I'd say null. That's a good answer. So that's going to be looking at null or null pointer. And that's how our linked list looks, all right? That's how our linked list looks. So kind of the most important thing to remember is that when we're making nodes, we need to have a struct for them. You could use a class if you wanted to, but we're only storing data. So in here, we're going to have a node next. That's a little bit of a recursive element there. And then I guess we're going to have our type, whoops, data. All right. So notice here we've got a node inside of a node. That's a little wacky. But that's what our singly linked list looks like there. All right. So this could be for an SLL, and we'll just leave it at that. So when we're in the code doing that, kind of talk about what I made last time. The first thing we did was this, right? We actually made the struct for our node, and it looks exactly like it does here on our whiteboard, except I used T instead of type. So maybe we can change that up just for fun. Now, templates kind of get me too every now and then. So I did try to compile this last time and I got an error. Why is that? That's because I didn't specify what template type this node in here is. So I have to indicate that this node is of the same type. Isn't that a little wacky? I think so. So that's our struct, all right? That's what our node looks like. And then down in here, I may have forgotten to do this last time too. We have the node head, right? That's kind of what is going to start off our linked list. Here we have it over here. Right here we have it. Whoops. Here we have it over here. And it's actually going to be this node, all right? It's going to be that node. So right now it's not going to be looking at anything. And the most important thing here is recall that we made this a template type. So we're going to have to indicate that this node is going to be of the same type of the class. And then now we're prepared to kind of develop all of our little member functions here. And so I kind of put them all in here already. We're going to do them kind of one at a time. And then tomorrow, or if we get to it at the end of class today, this is kind of the hard part of the assignment. We're going to do a sort list function, and we're going to do a swap nodes function. All right, so these are kind of the final bosses of our linked lists. This is kind of the final boss. But the rest of these are going to be kind of a piece of cake, hopefully. I might add a few other things in here, like maybe, let's see, I would probably want to type at. I'll talk about that later. And I probably want maybe a few operators in here just because we always do some operators. And to start, I'll do a, maybe a node T pointer operator bracket. We'll see how that goes. We'll cross that bridge when we get there. All right, we'll cross that bridge when we get there. So we're going to start with a few things. For one, we'll start with our default constructor, right? So there's our SLL there. And so I'm going to define all of these outside of the class because I know you are currently working on the template assignment. So I might be able to help you out here by kind of showing you how the syntax works. It kind of might make some things click for you. So if I want to declare this outside of the class, I'll just copy it down here. And so the first thing that I'm going to need is a template, right? The template comes with it, and we can name it whatever we want. Yeah, I know a lot of you had some syntax errors. So, you know, templates are really good at that. So I'm going to see if we can do this all together. Maybe for fun, I'll even do a friend ostream and operator. That one's going to be fun. And we'll have an ostream out and maybe an SLL. We'll get to that when we get there. All right. So I'll kind of throw these in here too, because I know that I'm making you do, I think, both of these for the other assignment too. All right. So I'll kind of throw those in there. But the first thing we're going to do is if we're defining it outside of the class, we need that, right? We need to bring the template with. And then we need the type. What is it? Well, it's an SLL. It has no type. That's the constructor. But there's a very important thing here we need. We need the scope resolution, right? So usually you would do it like this, but we're not quite done. Because it's a template type, we have to specify that this scope resolution belongs with that same template. And once we get to that point, we can do our default initializations. So I'm probably going to initialize my head to be null pointer. I already kind of did it up there, but just to be complete, we'll have that initialization there. And then our size will probably be 0, right? Then we actually don't need anything in here. We can just say done. We did our initializations. There's really not much left for us to do. All right, so that's our default there. Now, singly linked lists, in a way, are going to kind of be like vectors. We could develop a constructor that takes a list and, inserts all that stuff. But I think if I'm going to want to do, say, for example, an SLL that takes maybe an array. So it takes maybe a T array, something like that. I think I'm going to want to use some of these functions down here, like maybe push back, right? I could just do a for loop and call push back a bunch of times. So the way to think about a linked list is instead of kind of developing this constructor first, let's actually think about it like we're just going to insert things one at a time. So we'll kind of move on from this constructor part, and we'll come back to it later. Now we're going to work on our rule of 3 stuff. So this one is going to have to deallocate our list. All right. This one's going to have to deallocate our list. Now this is the copy constructor, right? This one right here I'm looking at is the copy constructor. So it actually doesn't have to do deallocating, but it does have to make a deep copy of the parameter. And then this one here has to do both, right? This one's going to have to do a deallocate, and it's going to have to make a deep copy. So our rule of 3 here is there. Here's there, there's here. Here it is. And it looks like we're going to have to call deallocate a few times. Looks like we're going to have to call deallocate a few times. So the thing that I think I want to work on first is maybe this function. Are you guys okay with that? So let's say I develop this clear list function. It looks like I'll be able to call it both in this and in this. So let's start with that. So now my computer will freeze. I have a little bit of lag. Are we back? I lagged a little bit there. Let's see what looks like we're there. Yeah, not so bad. Thank you, thank you. All right, so we'll continue on here. So like I said, if I develop this function, it's going to deallocate the whole list. We're going to be able to use it quite a few times. So we're going to work on that one first, and then we'll come back to these ones. So we're going to learn how to completely deallocate a linked list, which means we're going to have to go through each of these elements one by one and call delete. We can't use a delete bracket here because they're not side by side in memory. So we're going to have to go in here, deallocate this one, go to the next one, deallocate this one, go to the next one, deallocate this one, Now we're at the end. No more deallocation to do. So we're going to have to kind of step out of the box here. And we can do this recursively, or we could do it iteratively. So maybe we'll do both, huh? Maybe we'll do both. And you'll be able to help me out here. You'll be able to help me out with some of these, all right? So we're going to do both. We're going to do both. Now this one won't be static because I want to have access to the head node, but in the recursive one, I'm going to want to have access to this node, and I'll show you why. So let's bring this stuff down here and let's get to work. All right, so we're going to do the iteration first, and then you'll help me out with the, you're going to help me out with the recursive one. All right, so the very first thing I need to do is kind of just copy this little bit here, right? Since I know that one's good, I'm going to bring it here. Except I'm going to have one little tiny problem. And that's that I want my type to be in the front of it. All right. Now this is the most important thing when it comes to linked lists. All right. Whenever you need to do anything with a linked list, and when I say anything, what do I mean? Insert, deallocate, delete, find, if we can access a node, etc. You will always want a traversal node. Now, the traversal node is kind of like an alias a little bit, but we need it. Is to go through the list without editing the head pointer. All right? Now, maybe I can take out this little deallocate here, because you'll see. But we're going to be using this traversal node kind of up here pretty soon. We almost always are going to need some kind of traversal node. Some node that's going to allow us, if I could help visualize it for you. Let me make a little thing here. Without editing the head node, I'm going to want to have this thing here so that I can look at the head, or I can move to this one, or I can move to this one without actually changing the head node at all. So the traversal node will kind of help us get through that list. Yes, so we're going to make a temporary node that's different than the head node. And that's because we're going to need to be looking at one of these elements without actually changing this, right? So kind of the most important thing to note here is if I change this node here to look, say, at maybe this one, you agree that I no longer have access to this node, right? As soon as I change the head to look at the second element in this linked list, I no longer have access to this element here, right? You agree with that. So that's the whole reason that we need that traversal node, so that we can maintain the integrity of our head node here, maintain that it's always going to be looking at the head, and we're kind of going to make an alias, right? I've always said that aliases are bad things, but in this case we're going to use them correctly, and that we're going to make a brand new node so we can get through this list safely. So we're going to have a traversal node. So if we're going to clear this list, I kind of just want to show you how this traversal node is going to look. So I'm going to make a brand new node, right? Can anyone tell me what that node might look like if I'm going to declare it? I want it to be named this, all right? So I'll give you that. But what do I put out front if I want it to be the same type? If I want it to be the same type as the head node, the same type as the linked list. it will also be a pointer, so I'll give you that. Almost, right? Cherry, you're almost there. We're just going to need to throw that T in there. But other than that, that's good. All right? That's right. So this is going to be our traversal node. All right? And so I need to find a starting place. So the very first thing I'm going to do is I'm going to alias it, avert your eyes. We'll go to the head to start, right? We'll go to that head to start. We need a starting place. We need to get into the linked list somehow, and that's how we're going to do it. So avert your eyes. The alias here, it happened. But don't worry, because we're going to be editing the traversal node, but not the head node. Not yet, at least. So I'm going to kind of wave my magic coding hands here a little bit and give this one to you. And as I said, you'll help me with the recursive one down below. So I want to deallocate every single list in here, or every single element in that list. I'm going to want to deallocate it. So I'm going to need something like, say, a while loop. So I'm going to say something like this. While, say, our traversal node does not equal null pointer. Which means while the list is not empty, in a sense. So notice if the head was null pointer, right? Just like up here in the default constructor, we've initialized it to be null pointer. If the list is empty, this traversal node will be null pointer right off the bat. And then whatever code's in here, we're not going to do anything with it. All right, we're not going to do anything with it. But if it's not null pointer, then we're going to want to deallocate it. So there's a few things that we're going to have to do here. So I'm going to give some code here. I want to see how inclined we are, or how much this is making sense. So I'm going to type some code, and I want you to tell me if you think there's anything wrong with it. So I know that I want to deallocate this node. And then if I want to get to the next node in the list, this little bit of code is going to be kind of confusing, maybe. But I want the traversal node to be equal to whatever the traversal node was, its next pointer. Now remember what this arrow does. This is the exact same thing as dereferencing it and calling a dot operator, all right? So this gets us to the next node. Do you guys see anything that's wrong with this list, with this code potentially? See that there's anything wrong here potentially with this node, with this list, with this code? Well, Cherry, what I'd say about that is these are actually all single elements. These are all single pointers. So the delete bracket is not a requirement in this, actually, which is kind of, I don't know if it's nice or not. But when it comes to linked lists, we're usually not going to use the bracket. But this is a little bit tricky. So notice here that I've deallocated this pointer, right? I've deallocated it. And then notice here, I'm accessing an element from it. So, Migisto, to answer that, if there's something next to it, think about it this way. If we're here, and I delete it, and then I say it's equal to the next, it's going to be equal to, say, null, right? And then it'll come up here and evaluate this. And it will say, hey, the traversal node is now null, and the while loop will break out. So this code is almost 100% fine, except that this bit here has been deallocated. Do you know what kind of valgrind error this generates? Does anyone know what valgrind error this will generate? What it will tell us that we've done? And the thing I'm saying here is we've deleted this. So this is, yeah, a dangling pointer. And dangling pointers give us, yeah. I mean, yeah, so you're both right. The one that Valgrind says, it says invalid read. It means we read memory that doesn't belong to us. So this will be an invalid read. So in order to fix this, we're going to do this. All right, we're going to declare even more nodes. And I'm going to bring this one up here so that I can access the next node before I deallocate it. And then I'll actually deallocate it. And then I can just say here that this is equal to the next node. So this will move us along to the list. All right. And so kind of what does this do? Well, if we're going to look at the whiteboard here, we're going to have a few things. Say we're going to have the next node here as well. And the next node's going to have its own little arrow. I know I spelled that wrong. I'm sorry. So the very first thing that I'll do is I come into the function, right? I come into this function and I say, hey, the traversal node is equal to the head node. So that kind of generates this little picture here, right? Where we have the node head is looking here and the traversal node is looking here. And then so we go into the while loop and we say, hey, does this equal null? Is this null? Is it null? Is this null? It says, no, it's not. It's not null. So now we're going to make this pointer to look at the next one. That's the very next thing we'll do. So I'm going to take this next node over here, and I'm going to point it here. And then the next thing I do is I delete it, right? I'm going to kind of just move it here. I delete it. And now traversal node is no longer looking at anything valid. The head node is still looking at it, but we'll get to that part later. And then we say, hey, the traversal node is equal to the next node. So we'll grab this one here, and we'll move it over. So then we'll say, hey, is the traversal node null? No, it's not. So we'll move this here. I'm going to move this stuff. And then it's going to say goodbye. It's going to delete it. I'm just kind of moving it over here, obviously, but we'll delete it. And then we'll say, hey, the traversal node is equal to the next node. And we'll say, hey, does this equal null? No, it doesn't. So we'll delete it. And then we'll say, well, no. Hold on. I skipped a step. The first thing we say is the next node is equal to traversal next node, right? So now it's looking at null. And then we delete it. And then we say the traversal node is now equal to null. And so then we'll ask, right? I mean, we set the traversal node equal to the next node, and then we check in the while loop, is the traversal node equal to null pointer? Yes, it is, so now we're done. And kind of here at the end, I'm going to say our head node is equal to null pointer 2, because we're completely done. And then maybe I'll say size is equal to 0. So it's kind of a cute little function. Do we have any questions about how that worked? All right, this is going to deallocate a whole linked list. This will deallocate our whole linked list. You're going to want to save this code for the assignment. This code will help you in the assignment. All right, make a note. Here it is. How do I deallocate my deck of cards? That's how I do it. All right, so now let's do the recursive version. The recursive version. So, looking at this, what do you think our base case is? When does the recursion stop? If we were going to convert this iterative function into a recursive function, what do you think our base case would be. And the hint for that is, let's say, look at that while loop there. Yes, that's exactly right. That's exactly right. So we'll say, hey, you know, if this node, say, equals null pointer, then we'll say return. We're done. Now, notice that this is a void function. Therefore, we're not actually going to return anything here, right? I know some of you, when it comes to recursive function, what you return can be a little confusing. This function is still recursive, even though it's not going to return any sort of type. We'll just type return here. All right. Else, we know that the node is not null pointer, right? Else, we know that it's not null pointer. So we're going to have to do a few things. So I would say, what's the first thing we should do? Before we deallocate anything, what's the very first thing we should do? And you can kind of look up at this one here to get an idea. Before we deallocate anything, what's the first thing you think we should do? This is going to be loop clear list. So it's going to be recursive clear list. Yeah, well, I would declare a new node pointer. Yes, I think that's what you meant. And the main thing I want to do is I want to save what the next node is, right? Because if I'm going to call delete on this, if I'm going to call delete on whatever this node here is, I'm going to want to make sure that, yeah, that's exactly right. I guess there's probably a little bit of a delay, but attacker, you're right. Now, I'm just going to clear something up a little bit. Notice that this one is a non-static, therefore it has access to this head pointer. Now, with a recursive function, it would be almost no, you're right. You're right. You know what? I'm going to edit it. We can make this recursive without doing anything. You're right. Let me fix it here. What am I going to do? So we'll actually use the head node instead. We'll use the head node here. That's fine. Because we're going to just use it kind of as a traversal node. If we're going to be deleting the whole linked list, I know in general we said that we don't ever want to edit that head node. But the fact is, if you want to kind of reconstruct this linked list here a little bit, if we delete them in order from head to back, we can kind of do it. Sorry, it's a little janky there. But what we can do is we can kind of delete this one here. Right? Now we don't need it anymore, and we can actually move the head up if we wanted to. All right, so we'll do it for this function. But for all the rest of our functions, we're going to be using traversal nodes. I just want you always to remember that. If you feel like you need to use a traversal node, it probably is not a big deal. All right. So we're going to stick with our same base case here. If the head is equal to null pointer, that's our base case. And then we're going to do what attacker said. That is, we're going to do the next node. So in that case, we'll say head. Now I'm going to stop using this silly little syntax, and I'm going to use my arrows because I like that. So now that we've done that, I'm going to say delete on our next node. Not our next node, but our head. Let's deallocate the element. And then we'll say head is equal to the next node. And then we'll call clear list again. That one's almost cuter than this one, right? This one's kind of, I don't know, it looks like there's a lot going on here. This is do the exact same thing, right? So if the head happens to be null pointer, it'll return. Else, we know that the head is not null. So we're going to go ahead and save the next node. We're going to delete whatever the head was. We're going to say, hey, the head now equals to the next node. Notice it is still pointing to the head of the list. We haven't really changed anything. And then we'll just call the function again. Are you okay with that? So there we go. We've got a recursive clear list, and we've got a loop a loop clear list. We've got 2 of them. So let's go ahead and make our destructor. Yes, here it is. Does that answer your question, Cherry? That's kind of the most important thing here. Notice that this next node here is still kind of a traversal node, isn't it? It's still kind of a traversal node. We're going to need something to go further in the list, you know, before we delete anything. But it's right here, isn't it? So almost this code here is identical to this code here. Pretty much identical. And then the looping is a little bit different. So now I'm going to do my destructor. Let's kind of do all of these. We'll do the destructor and we'll do the operator now. All right, the destructor is very simple. It's going to be a very easy function, very easy member function. So we'll call this our destructor. And I'm just going to put my tilde there, right? And what do I do in here? I'll just call clear list. Whichever one works, right? We could even call both if we wanted to. But that's not necessary. So that's a great question, Cherry. Before I do that, I want to do one thing here real quick. And I just want to say size minus minus because I want to kind of keep track of the size here. I always forget to do that. We don't really have to with linked lists, but I want to for this one. So here's the most kind of important thing to remember about that is the next node. Let me kind of point it out for you. So that pointer, this is kind of hard to visualize, but this object here specifically lives in this pointer. And so we can initialize this pointer to contain an address, right? If the pointer contains an address, it contains, I'm going to use a different color. This is kind of hard to see. That's even harder to see. I think white's fine. So this whole object lives inside of this pointer. And so this pointer can contain an address for an object, or this pointer can contain null. It can contain null. And so the idea here is that, let's see if I can... You're wondering where next is initialized? Well, next will be initialized likely in these functions. Next is likely going to be initialized in our insert functions. When we start inserting things to the list, you'll kind of see how that works. But the most important thing to note here is this is either an address or just null. So next doesn't necessarily have to be initialized. I mean, it does, but it's either null or an address. It's either one. And so you can see here that as long as this is null, we'll know that we can get to the end of that list. So after I finish out this, what am I doing? After I finish out this destructor and this assignment operator, well, let's not do the assignment operator yet. Let's go ahead and do some inserts instead. You're right. Let's do some inserts instead. Maybe I can help. So the current node won't work until we do the insert function. In a way, yeah. Notice in both of these deallocate functions that we've made, it's likely that just if we use a, I mean, we can come down into main or go up into main, and we could make an SLL t, not t, int my list. We could do this. What does this call? This calls the default constructor. And in the default constructor, head will be initialized to null pointer. And so when we actually call the destructor, we'll call clear list, and it will say, the traversal node is equal to head. What does this mean? Traversal node is now equal to null pointer. And then we'll say, while traversal node doesn't equal null pointer, well, the traversal node does equal null pointer. So this whole block of code is skipped, and then it's done. So there's going to be no problems. But let's do some inserts so you can see how it works. Let's do some inserts. We'll come back to our assignment operator in a little bit. Let's go ahead and do the push to the front first. Let's do the push to the front. So this is going to put an element at the head. It's going to put an element at the very beginning of the list. So let's go ahead and make our template function. This is going to be push front. So we're going to have a template type name t. And in this template type name t, we're going to pull out whatever type this is. That's probably a void. And then we're going to call the SLL, right? Scope resolution operator. As long as it's at that same template type, we'll call the push front. And we're going to pass in some t item, whatever that element is. Item to insert, if you want to call it that. So this one is the easiest, right? We're just going to put something at the beginning. So the easiest way to do that is the first thing we need to do is make a new node. So the way that we do that is we'll say node t new node. Now this makes a pointer, right? This pointer will probably initialize it to be null pointer to start. And then we actually have to do the allocation. Is equal to new node t. So we actually allocate it. Allocate the pointer. And then we're going to go inside of that pointer and we're going to say, hey, that data is equal to the item. And then we're going to say something like, we're going to do an initialization here. So we might say new node equal next is equal to, say, maybe null pointer. Notice here that it gets initialized. So whenever we insert a new node, we'll go ahead and initialize that next thing. Except we're putting it at the head of the list. So what do you think I'm going to point next to? If we're going to put it at the very beginning of the list, what do you think I'll point next to? Let's see. Shouldn't we move the head to point to the element that we're putting in? Yes, that's correct. You're right. So we'll say something like this down here, but we have to do something first, right? That's that. So let's make the little whiteboard of that. Let's make the little whiteboard of that. So what does this do? This inserts an element, or this inserts the data. And then we'll point it to the head. And then we'll adjust the head to now look at the new head. So let's make the whiteboard of that. So let's pretend I have this 5 down here. And I'm going to put it in the list. So we're kind of looking at this. I'm going to move these out of the way for now. So let's pretend that we're looking at this list and we say, hey, we need to make a new element. We're going to insert a new element. So what we're going to do is we're going to call allocate, and I'll kind of give birth to this little element here, right? Down here at the bottom. So I've allocated this node, and then I put the item to insert inside this bit, right? So we put the 5 in there. And then I said this next node is going to be initialized to look at that head node, right? So now that this next node, that's this bit here, new node next equals head. Now that that is at the beginning of the list, I need to then move this to look at the actual one. So we just had to update some pointers there. In fact, how many pointers did we have to update? That's a question that we'll ask. How many pointers did we have to update? We had to update this one and this one. So 2 pointer updates. We'll actually kind of keep that in mind. We'll keep that in mind. So let me ask this question. This is always important to remember. It'll help you when you code, I think. When inserting elements, how many pointer updates are there? Well, in the SLL, we're going to have 2. That's going to be, well, it's going to be the next node of the new node, and it's going to be the node that was previous to that. In the sense of this thing here, that pointer update was actually the head node. It was actually the head node. Now, if we were going to insert it in the middle of the list, we're going to have to adjust this node here to look at this one, and we're going to have to adjust this to look at this one. So that's still 2 updates. That's still 2 updates. All right, so in a singly linked list, when we're inserting an element, how many pointer updates will we have to do? 2. Check my notes here to make sure that that's on par. Yep, that's right, that's right. All right, so now we're going to do the other one. We're going to put it at the end. We're going to put it at the end of the list now. So let's do the pushback function. So what do you think kind of the idea of this one is? What are we going to have to do? Do you have any ideas? What are we going to have to do? It's going to work kind of the same way, except there's a little bit something else going on. So I would say this is likely something we'll have to do. We'll probably have to make a new pointer, and we'll probably have to allocate it. Right? Now, where are we going to put it, right? We have to put it somewhere. Yes, we're going to have to iterate through the list to find a null. So what, let's see. Yeah, a new pointer. So you're kind of right. So the first thing I want is probably a traversal node. So let's do that. All right. And what will I initialize this to? What do you guys think? If I got to start it out. If I'm going to start it out, how am I going to do it? I do just kind of want to look at the head, right? Yeah. That's what I'd say. We have to start it out. So we're going to just start at the very head. The thing to note there, Cherry, is that there might not be a next one. The head actually might be null. The head actually might be null. Or the head's next might be null. So there's actually a few more cases that we'll have to keep track of in this one. So the first thing we'll do is first see if the list is empty. So if we know the list is empty, it's going to be this. All right. If the list is empty, then we know that that traversal node will be null. Up here, I'm going to do a few things real quick. I'm going to do kind of the exact same thing that I did in the previous one. So I'm going to say that the data, we're going to put the data in the node. And what do you think I'll initialize the next to be? Now, this one is going to be at the end of the list. This one is guaranteed to be at the end of the list. So what do you think this next will be initialized to? Null, that's right. So we'll make this one null pointer. So notice the difference up here. If we're putting it at the front, then we'll make it the next point to the head. But if we're putting it at the back, we'll make sure that this is pointing at null, because it'll be at the end. All right, and then we'll get our traversal node going. We're going to need one of those to go through the list. Then we'll check to see if the list is empty. If the list is empty, then I'll just say, hey, the head is equal to the new node. And we're done, right? And notice everything's nice and initialized, right? The head's going to contain the item, and the next is going to point to null pointer. But else, the list is not empty. We're going to have to make our way through that list. We're going to have to make our way through that list. So we could do this recursively or with a while loop. All right, we're going to do, I always do the while loops. Recursion really works nicely for linked lists, always. So you could definitely make this recursive, but we're going to do the while loop for now. All right. And so in order to do that, I'm going to put the while loop here. I'm going to say, hey, while the traversal node next does not equal null pointer. Now, does anyone know why this is necessary and why this will not be good enough? This one's kind of a bit of a hard question, but do you know why I have to do this? I have to put the next there instead of this. In the deallocate function, that was enough. But in this one, it's not. Does anyone have an idea of why I need to check for the next node? And it's a very important kind of idea to remember here. So the way I would say this, let's see if I can whiteboard it. So how are we going to do this, right? So we're going to bring in our traversal node. I'm just going to use this arrow for now. Here's our traversal node. It's at the head, right? And we'll say, hey, does the next node here, does it equal null? No, it doesn't. So we'll actually move it over. And then we'll check the next node for null, and then we'll move it over. And then we'll check the next node for null, and then we won't move it over. Now let's pretend we were checking for nulls. Say, hey, is this node here? Is this node null? Nope, let's move. Is this node null? Nope, let's move. Is this node null? Nope, let's move. Now we're looking at null. So then I might allocate it. But my question is, how am I going to link it to this one? How am I going to link it? So, yeah, maybe that was a little bit of a confusing question, but so tell me if I need to spend some more time on this. But I need to actually do it from this node because I have to link it in here. That's like the most important part. I have to link it in here. So let's pretend I do this, right? I have it somewhere. I need to like bump it in here. And I need to say, hey, from this pointer, I'm going to put this one here. If I'm looking at null, I'll just have one that's floating out here in the void. It was never linked into the list. It'll just be floating around out here in the void. So I actually need to link it from the list. So I need to look for next because I need to link the new node into the list. So I'll say while the traversal node next does not equal null, I'll say traversal node is equal to the traversal node next. Move along our list. We'll move along the list. So say, hey, the next is not equal to null. Well, I will set you equal to that. And then I'll check again. Is the next equal to null? Nope, I'll set you equal to it. Eventually, when the traversal node next does equal null, we will say the traversal node at the next pointer is equal to our new node. There's a few things I want to do in here. I keep forgetting to do it. I want a size plus plus. I want a size plus plus. All right, so I'm probably melting your brains a little bit here. But are we kind of following along here? That we're just going to kind of while loop our way to the end of the list until we find the one that is the last element, and then we'll link it. Okay. Now, in your assignment, you're going to do the push front. In your assignment, you're not going to have to do a push back, I don't think. But just so you can see this happening, right? If we're going to go to the end of the list, we're going to have to traverse our way there. We can't just use the brackets. Say, hey, at the X element, please set this equal to whatever. We can't use brackets. We have to go to the end. We have to go one by one. All right, so we're moving along here. Now I'm going to finally do these two functions. First, I'll do the operator overload. And this one will be probably the... it'll be much easier now that we've done all these other functions. So let me grab my stuff. All right. Now this is going to be a copy of the list. Now we have to make a deep copy, but guess what? I've got all these cool functions now. So the very first thing I'm going to do, I'm going to clear my list. Clear the list, right? We have to deallocate. Didn't we say that? We've talked about this plenty of times already this summer, in that we have to deallocate first and then make a deep copy. So the very first thing I'll do is call clear list. That's going to clear the left-hand side list. It clears the left-hand side list. And then the next thing I'm going to do is I'm going to make a deep copy. Now this could get kind of disgusting. So I'm actually going to use my functions that I now have. So how will I do that? Well, I'm going to make a traversal node for the copy linked list. I'm going to make a traversal node for the copy linked list. Now, in my clear list R, I believe eventually I'll set head equal to null pointer and size will be 0. So I'm not going to worry about resetting them here. So the head is already null pointer. And the size is already 0. So we're good. After we call clear list. And now we're going to do this. We're going to make a traversal node for the copy linked list. So I'm going to make a node, T, traversal node, to go through the copies linked list. And I'm going to call it the traversal node. And what's that going to be equal to? If I want to start it out at the copies linked list, what do I set it equal to? What do you think? What do you think I set it equal to? I got to start it out somewhere, right? If we're going to start it out somewhere, where do you think I'll start it out? What could it be? The head, right? But which head? That's what I'm asking. Which head? It's going to be this one, right? I want it to be the copy head. All right, so now we're dealing with other singly linked lists. The other one's head. And tell me if this bugs you. All right, I'm going to kind of wave my magic my magic coding hands here. I'm going to say while this. Now, notice here I'm not doing any linking, all right? In the insert, I had to do a link here. So I'm going to look for the next one. But I'm just going to do this one like this, all right? Since I'm not actually going to do any linking inside of the copies list, I'm not going to worry about checking the next one. I'm just going to look at this one. I'm going to look at the actual node and not the next node. Since we're not doing any linking, there's no need to do this check, all right? So just kind of remember that. You need to look for the link. You need to be able to link things. And if you need to link things, then you have to do this check for the next one. This one here, we don't have to do it because we're just going through the list. We're just going through it. We're going to go find something. Now, if I found a node here, I'm just going to do this. What do you say? How's that? Are you happy? You think we're done? So we'll start at the head, right? And then we're just gonna kind of find elements and put them in. This makes a deep copy, by the way. Just so you know. We kind of already coded this. This makes a deep copy. Notice that there's an allocation that goes on here. Here's the deep copy. And then we go put it exactly where we want. Notice I'm not doing this. Notice I'm not calling copy.pushback. That's not allowed. I'm calling pushback on this, if you'd prefer to see that. I'll put the this here. That always, I feel like that kind of helps some of us realize where the left-hand side list and the right-hand side list is, right? Oh, there's one more thing I need to do, though. I'm gonna get an infinite loop in here if I don't do this. All right, I'm gonna get an infinite loop here if I don't do that. All right, so this is our assignment operator overload. The very first thing we'll do, we'll deallocate our linked list. We don't need it anymore. And then we will make a traversal node for the copies linked list. And then as we go through there, say while it's not equal to null pointer, we'll call pushback on the this object, whatever that data is. Notice I'm dereferencing here. So we're making a deep copy. And then I'm going to send the traversal node to the next one. Eventually it will it'll while loop itself out and we're done. All right. Now let's do the easiest one in the book, folks. Let's do the easiest one. Look at us. We're moving along here, no problem. I might kind of take a little pause here to just go over the assignment. So let me kind of do this easy one, and then we'll kind of stop for the day. And tomorrow we'll kind of come back in here and finish these out. All right. This week I'll be happy to schedule some calls with you guys since we are kind of running out of time here. Assignment 9 will be definitely a fun one. So I'll be happy to schedule some kind of out of office hour calls with you guys so we can work on it together. I will prioritize finishing linked lists tomorrow, and then maybe on Thursday we'll spend just a little bit of time talking about stacks and queues. I kind of forgot about those. But those are not hard at all. So let's finish out our copy constructor. What can I put in here? What do you guys remember? What can I put in here? What is it? What am I going to put in here? I want to do 3 things. What do I put in there? I'm going to do this. But what else can I do? Someone's got to know. What can I do? Yeah, that's right. So Cherry's on the right page with that, right? A little delay there. What else can I do? Yep. Shortcut works here as long as our operator overload works. All right, so that's done. All right, so as long as this one works, we can just initialize our stuff and then do that. All right. So I'm not going to have time to go over the whole assignment, so we're just going to stop here for the day. I'll upload this stuff. Tomorrow we'll come back and look at it. For the remaining 9 minutes or so, I'm just going to briefly introduce the assignment to you. All right, I'm going to briefly introduce the assignment to you. It's the last assignment we have. I'm very proud of this assignment. This is probably my favorite assignment of all time. I'm a card guy. All right, I don't gamble. I just play canasta with my grandparents. That's what I do. All right, so I know quite a few card games. So in this assignment, we're making a card game. Now, what's awesome about this is that, guess what? You guys already kind of coded a card class earlier this semester, didn't you? So part of this assignment, you're going to be able to kind of go in there and maybe take some things out of there and implement it in this assignment. Man, I'm so nice to do that for you guys. I can't believe that. But the linked list stuff will definitely be some work. So April 2021, maybe a little old. I'll try to update that. Doesn't really matter. But we're going to play War. Now, there's a bunch of different ways to play War. This is like the War I played when I was a kid. All right, so you and your sister get together. You each have half the deck, and you flip cards over one by one. Whoever has the highest card wins the pile of cards. All right, so for those of you who don't know what War is, you can go to my YouTube channel. I have a video talking about this assignment in depth on my YouTube. You're going to have to kind of scroll down a little bit before this class started. But you can find it there. Now, I will say this assignment was done in the past. None of the other assignments you've done this semester were previous assignments. This one is. Now, this month, I'm going to moss all of the assignments. All right? I talked about that at the beginning of the semester. That's how I check for plagiarism. So if anybody in the class had sent their code to somebody else and they didn't change it up enough significantly, Moss will tell me that, all right? So I'm just warning you now. I want you to do this assignment on your own. You could definitely go find someone who did this assignment previously, but I will Moss your assignments with all of the previous assignments. And if I find a match, not only will I submit an academic misconduct report for you, but I will also submit an academic misconduct report for that person who already passed this class. And you don't want to do that. I've seen people have their degrees revoked for doing stuff like that. Now, I'm not saying that's this extreme. I'm a nice professor, okay? I promise I won't, revoke anybody's degree, but do this one on your own, okay? You can go to the YouTube channel and watch the video if you want. Here I explain the rules of War, all right? Here I explain the rules. You can read that if you'd like. But overall, there's 5 files. You only have to add code to one of them, maybe 2 if you want. So let's look here. There's a whole bunch of files here. So there's the player classes. I did these completely for you. You can look at them. They are all very short little functions. You can just read them and look at them to see what they do. All right? You can just look at them to see what they do. All right? It's pretty simple. Here's the player class if you want to go look at it. All right, I did this 100% for you. Now, you're only responsible for a card and a deck class. Haven't you already kind of done something like that, right? So here's the card class. Probably looks very similar to your other card class. Now, these you'll have to change up a little bit, but pretty much every other function you can copy from that original assignment. Here's your deck class. This one is not using a vector. Guess what it's using? a linked list. All right, it's using a linked list. So notice all the functions that I'm going to kind of work with you on are in here. Now, I suggest that you can add this function if you want, all right? You're allowed to add this if you want. It will help you. Just kind of read the assignment. I'll tell you about that later, what you can do with this. But if you recall, sometimes the bracket operator returns the actual reference, right? Notice I'm returning a pointer here. That's an address. It returns the actual reference. This one here is going to return just a copy of it. So this may help you later in the assignment if you want, but you don't have to put it there. Now everything in here is already kind of put there for you, all right? So you just can go in there, put your code in there. It will compile right off the bat, and I gave you quite a few operators already, or quite a few functions already. So basically 2 players will just throw cards at each other and they'll claim them. There's a lot of inserts going on. There's a lot of removing cards from decks going on. If I were to run this function for you, this code for you, guess I'll log into Bobby real quick. In next class, I'll do my best to take some more time to talk about it. I just kind of wanted to show you what you're doing to see if there's any real main questions to start. But for the most part, you can watch that video and read the PDF, and that should be enough for you. But like I said, I'll do my best to come back to it tomorrow. The clock is ticking here on us. All right, so if you just load everything up there, you can go to your test or whatever directory you have. Now, if you were to compile it like normal, you could do that. You can say std equals C++11, and then you type main.cpp player.cpp card.cpp. Now that will work, though I made it very easy for you. I made something called a make file. We didn't really talk about that this year, but the make file, you can just type make, and it will do that for you. All right, so every time you want to compile it, just type make, and you'll see that it types it in there. I gave that to you. All right. So when you type make, it compiles it, and then when you're ready to run, you can hit /a.out as always. And it's going to ask you for a seed. Now, I originally made this game randomized, but since we're using lovely software CodeGrade, I needed to make a way for it to not be random. So all you have to do is go to Web Campus. All you have to do is go to Web Campus. We're almost done here for today. I won't hold you too long. But come to Web Campus, go to the files, and I gave you the seeds that you want. So go to files here, look at assignments. No, it's a little tiny. Go to final project. In here you'll see seeds.txt. So you'll notice that I've included 3 seeds. One gives you different results. So if you just highlight one of these, you can place it here. It's like a Minecraft seed for those of you who play Minecraft and stuff. It's just a seed. You enter it, and then it will ask you if you would like to print the game, which you can, or you don't have to, but I will. So I'll press yes. And then we'll kind of go through it just a little bit, but you'll see the players are just taking turns over and over again. So let me go all the way up to the top. So here's the player 1's cards, here's the player 2's cards. They're shuffled, and then they each pull the deck off the top, the card off the top. So they take a D6 here, I think, versus an S4. D6 versus S4. Who wins? Well, apparently the 6 is greater than a 4, so player 1 wins. And player 1 claims 2 of the cards. And then they just go and go. If there's a tie, there's something that happens. But they just go, and they keep going, they keep going, they keep going. Until one of 3 outcomes happens. The outcome that happened here was that player 2 acquired literally all of the cards. So it's kind of a fun little assignment. Of course, you're doing the linked list part, which is no fun at all. But I think it's fun. Try to make it fun. Tomorrow, I'm going to spend some more time on it, and I'll even give you one of the functions. that function that I'll give you is this one. All right, I'll give you a version of this function, but you'll have an option to make it even better for extra credit. All right, so that's the one we'll go over tomorrow. But that's kind of that. So thanks for hanging in there with me today, class. Only 3 days left, so hang in there. I will see you guys all tomorrow, and I hope you guys have a wonderful day. Happy Tuesday to you, and happy late Independence Day to everyone here. Yeah, you're welcome. Have a great day, guys.